In this video, we will be talking about liquids, doing just a little bit of an introduction, introducing some properties about liquids and how they react to energy, as well as doing some examples that relate to these kind of problems. So, the first thing I want to discuss is sensible versus latent heat. Sensible heat is its change in heat that can be measured with a thermometer. And it doesn't include phase change, so I'm just going to include one phase. Now, latent heat, on the other hand, is change in heat within phase change. So these are certain properties about the heat that can't be measured just with a thermometer. So once we explain it, it will start to make more sense. Specific heat capacity is the amount of heat needed to raise 1 kilogram of substance by 1 Kelvin. Okay, so those are some basic properties about energy and how they affect liquids. We can also talk about latent heat of vaporization, which we use this equation here for. And we can define latent heat of vaporization as the amount of energy either absorbed or released during phase change. Okay, so if we were to imagine what this process might look like with our first kind of graph, we can imagine this process looking like this, going in a straight line from X to Y. Okay, so when we have this section here, I'm going to call this W. So this section here, so this is when we go from our liquid to our vapor up until our boundary point. This is sensible heat, right? Because we have one phase and we are transforming into vapor. And in the second part, from W to Y, this is our vapor region. And this is also sensible heat because we have only one phase. So when we spend some time in our W phase, that's when we are translating our liquid into vapor. We have both phases present. So this will create a tie line, which you should have already been used to in our PV and PT diagrams. So if we were to plot this with our pressure and our mole fraction, we would start with our liquid. Then we'd reach a kind of tie line point when we're transforming. And when we go from that point to vapor, it will look like that. Sorry, there's a mistake in my notes. Sorry, let me redo this. Sorry, this is a plot of temperature and energy. Okay, so our first one, we are starting at a lower temperature as we go to a higher temperature, because this is temperature plot here. So we're going to start with our temperature at point X, our temperature at W, and our temperature at Y. And this looks like this. So there is a sloping line up to our TW, and then we have our phase change, and then we have up to point TY. Okay, so there's an equation that we can use to define this. So in this process, so here's it better illustrated. This section here is sensible heat in our liquid phase. So this represents this portion of the graph, right, as we go from Tx to Tw. So those are the two temperatures that we're going to be using for the difference. And then this tie line here represents our latent heat of vaporization in this flat section here, because there's no change in temperature, but there is a change in phase, so we need to include that. And then we have this final phase here for our vapor, and that is a sensible heat process. Right, this is latent. And depending on if you are adding energy or taking it away, will depend on which process you are using. So if we're using X to Y, we are taking liquid and we're adding energy to the particles to turn into a gas. So in this case, this coefficient will be positive. But if we go from Y to X, we need to take away energy in order to turn the gas into liquid, so then it would be negative. Okay. So yeah, this is the equations that we use to create correlations between our conditions. We'll do a practice problem to further explain that. But basically, this is our standard form. Right, and if we want to use a correlation, we could use this form as well, which are all just different forms of this original equation here. So yeah, it'll make a lot more sense once we do some practice problems. Okay, so let's start with an example for our correlating vapor pressures. With this example question here, we're going to go through the process of using vapor pressure correlations to derive equations. So we have two different conditions, and I'm going to label them with different colors. All right, so we're going to write out our first equation with our first conditions. We're going to write it in the form of our ln pressure equals, so just going to move this around a bit. This is going to be okay, and when we do that, we're going to use our given pressures. So we have ln 781.7, and we have our A up here, and this is going to be over 425 Kelvin plus B. In our second equation, we're going to have ln 1167 equals to A over 440 plus B. Okay, and these A and B parameters are going to be the same for either correlation because the ratio remains the same. So what we do to relate these two, we're going to subtract equation 2 from 1. And what this does, this gives us, so using your Lon rules, you know that subtraction is division within the bracket. So then this is our first one over our second pressure. And then this is equal to, so both of our B's are going to cancel out. Oh, sorry, this is supposed to, actually, yeah, no, we're good. Okay, and then this is going to be A, so we're going to solve for A first. And then we have our first temperature, which is 425. I'm going to subtract 1 over 440. Okay, and again, our B gets canceled from this equation. So then this gives us, so let's solve for our values. Okay, so this is negative 0.4. This is equal to A times, so 1 divided by 425 minus 1 divided by 440. And this is 8.02139 times 10 to the negative 5. Okay, and we take our negative 0.4 and divide it by this number, and that gives us A is equal to negative 4,986. Okay, so that is our first coefficient done. And now, using this value, we're going to plug into either 1 or 2 to find our B. Okay, so let's use equation 1. So this is ln 781.7 equals, so now we have our value of A, which we just solved. And this is over 425 Kelvin plus B. Okay, and if we do the math for that, so on our left side we have 6.6614, and we have just negative 11.733. And this gives B is equal to 18.395. Okay, so now we're going to combine this into one equation. So this is ln P is equal to over T plus 18.395. Okay, and let's do this in our different form. Let's just move a couple things around. Let's put our B first because that's the form it wants it in. So let's start with our B and then minus our A over T. Okay, and this is our final answer for this question. Next, we'll be talking about Raoult's law, which is a law that relates pressure and vapor pressure with mole compositions. Okay, so using these equations over here, it was determined that our vapor mole fractions can be related to our liquid mole fractions using our pressure and our vapor pressures of specific components of mixtures. And this is the equation that we will primarily be using. Again, it will be better explained in an example, right? But we can use this to help determine compositions of vapor phases related to compositions in liquid phases. Right, so where our partial pressure of our composition is equal to our mole fraction of our vapor times the total system pressure, and it's equal to some kind of constant times the mole fraction of the component in the liquid phase. So I'll find us a question where we can do that. Right, and given vapor pressures and liquid compositions for a binary mixture, we can calculate mole fractions of a vapor phase. So we're going to go through this in an example to better explain what we mean. Okay, so starting with this question, we have 10 kilomoles of nonane and 22 kilomoles of decane, which are added into its own vessel. And after being mixed, the equilibrium temperature is 440 Kelvin. And under these conditions, the liquid and vapor phase coexist, where the liquid phase contains 24.6 mole percent nonane, and the vapor pressure of decane can be determined with this equation here. Okay, so first things first, we can use our information given in part A of the question, which we did previously. And we saw that at 440 K, which is the same temperature as our vessel in this question, has a vapor pressure of 167 millimeters of mercury. So we're going to need to convert that into kilopascals for this question. So let's start with that. So we have of our nonane, and that is equal to, so we have 67 millimeters of mercury, and to convert it, we know there's 101.325 kilopascals for every 760 millimeters of mercury, and this gives us 155.587 kilopascals. Next, we're going to use this equation to find our decane vapor pressure. So this was given by equals negative 5671 over our current temperature, which is 440 Kelvin plus 17.293. And using our lawn rules, this becomes, so it's negative 5,671 divided by 440 plus 17.293. And that's to the exponent of our E. And this gives us 81.807 kilopascals. And here we are going to use Raoult's law, and we're specifically going to be using this form right here. Okay, and this is going to find our bubble point pressure. So this is the sum of, our pressure is equal to each vapor pressure, so times its composition. So we're given our composition, so we can solve for this. So we have in our nonane we have our pressure, and we have the composition, which is 24.6%. And we have our decane pressure, and we'll need to find our our mole composition, which we're not given, but we can use this equation to find it. And then this will give us and this is equal to, sorry, I also made a mistake. This is not the one that we use. Apologize. So we're going to need to do our own separate calculation for this. So we're given our amounts, so we can find, let's just work with nonane, right? So in total we have nonane, this is equal to 10, and over our total, which is 10 plus 2, and our composition of nonane in this case is 0.3125. Sorry, this is the value that we'll be using instead. Okay, and this will then give us our pressure is equal to 105 kilopascals. Okay, we're going to move on to determine the molar composition of the vapor in this system. Okay, so if we were to illustrate this diagram for our pressure and our mole composition. So we found that for our nonane, we have a pressure of 155 kilopascals. And for our decane, we found that it was about 81. So if we were to join these, look like that. And we calculated that our composition for our nonane is 0.3125, which is about here, at about 105 kilopascals for our bubble point. So our bubble point is bordering our vapor phase, right? Because it's just about to become fully vapor. So that would be at this point right here. So this is 105. So we want to find what our pressure is first for at some point here, for some pressure here. And we are given this value for our liquid phase at this point, which is 0.24. This is 0.246 when we read across. So given that, we're going to use the equation from before, except instead of using our mix, we're going to use just for our liquid phase. So this is, so we want our total system pressure, and this is times 0.246 plus 81.807 times 1 minus 0.3125. And this gives us about 100 kilopascals. So that is what goes into this point here. Okay, so at 100 kilopascals, we want to find the molar composition of our system. So using Raoult's law, we can use this equation. So our total system pressure times our vapor phase mole percent is equal to our vapor pressure of our nonane, let me just change that, times the liquid composition of our nonane, which we are given. So if we just isolate for our vapor, gives us this equation, and if we plug in, so our vapor pressure of nonane was 155.587 kilopascals times, we are given 0.246, and we're going to divide it by 100, and this gives us an answer of 0.383. That's our final answer for our nonane molar composition. Right, and that means we can do our decane, which is 1 minus this. So this is equal to 0.617. All right. So now I'd like to take us back to finish a couple more examples that relate to the topics that we learned. Let's do one that relates to our sensible and latent heat diagrams. All right, so we used this kind of form to define our system. So let's work with that. Okay, so let's take a look at this question. All right, so we are going from a vapor phase and we are at a temperature of 250 degrees Celsius. So then we go to our, sorry, let me draw this a little smaller. Okay, and then at 177, here's where we're going to see our phase change. So it's going to be our latent heat as we undergo phase change. So then that means our temperature is going to be staying the same during this section. Okay, and this is when it starts to turn into a liquid. And then we have it fully in a liquid phase at a final temperature of 100 degrees Celsius. Okay, so I'm just going to start with turning these into Kelvin. So 250 plus 273.15, this is 523.15. We have 177.3 plus 273.15, and this is 450.45. So this one. And finally, we just have 373.15 Kelvin. So our temperatures are cooling, and since we are going from vapor to liquid phase, we are condensing our vapor. Okay, so we're going to be using this form. So this is our energy is equal to our liquid specific heat capacity. Actually, let me just change this. So we need our moles. This is times our liquid specific heat capacity and our first change, which is sensible heat from T, let's call this T2, T1, T3. So this is from T2, final minus initial. And this is plus our vaporization. And this is plus our vapor specific heat capacity, and then the difference between these two changes, which is T3 minus T2. And this latent heat vaporization represents this section here as our latent heat. Okay, so I'm going to write latent. Other ones are sensible. Okay, so we have 50 kilograms of pure nonane. So let's find our moles. So I believe we're given our molar mass. So our molar mass is equal to mass over moles. So we can get our moles equal to mass over molar mass, which is equal to, so our mass is 50 kilograms. And our molar mass is given by 128.255 kilograms per kilomole. And this leaves us with 0.38984 kilomoles. Okay, and now we're going to plug in for our equation. So our energy is equal to, so we have our moles and we want our heat capacity of our liquid. So this is 300. Oh, and we need to convert our kilomoles into moles for the sake of this question. Sorry, so let's do that because we want to keep our units consistent. So this allows everything to work out nicely. So then this is equal to 389.84 moles. Okay, and our liquid specific heat is 300. And T2 minus T1 is 450.45 minus our 523.15. Okay, and this is going to be minus our latent heat vaporization because, hold on. Actually, I'm sorry. So we can actually use our values as is for our kilomoles. We just have to change around the units of a couple other ones. And sorry, this is starting with vapor and then going to liquid. So we will use vapor first and then liquid specific heat capacity. Okay, let's try again. So let's use 0.39 kilomoles. And so we're going to start with 250 kilojoules. So we're just going to change this to kilojoules over kilomoles Kelvin. And this is times hour. So this is 450.45 minus 523.15. Okay, so that's our first term. And this is minus our latent heat vaporization because we are condensing, so we're removing energy. So this is 41538. And it was kilojoules per kilomole. Okay, and this is plus. So we have 300 kilojoules per kilomole Kelvin. And this is times our last change, which is T3 minus T2. So this is 373.15 minus 450.45. Okay, and all of this multiplied by our moles. So our energy is going to be negative. And then our final answer is negative 332,319 kilojoules. And like we said, our negative sign makes sense because we are removing energy in order to condense our vapor into liquid. Okay, and we also want to determine the pressure in ATM of the vessel during the phase change. So how would we do that? So we would use our vapor correlation. So we want to find the pressure, so this is our unknown, during the phase change. And we determined this equation was 4986 over T plus 18.395. Right, and we're going to use our latent process, which we determined was at 450 Kelvin. So we're going to put that in for T. It's going to give ln in kilopascals. Sorry, it's going to give pressure in It's going to give us pressure in kilopascals. I'm so sorry. This is 450.45 plus 18.395, and that makes our pressure equal to Okay, and this is equal to 1,519.39 kilopascals. We want this in ATM, so we're going to divide by 101.325, and this gives us, our initial equation used millimeters of mercury. Okay, so then we just need to convert it now. So for 1 ATM, we have 760 millimeters of mercury, and that means we have about 2 ATM pressure. Okay, and now we're going to move on to our last section of our question, which is part 3 of our Raoult's law stuff. So calculate the amount of liquid in the vessel at equilibrium under these conditions. So in this last step, we can use lever rule. So we want our liquid moles over our total is equal to our vapor for Y minus our liquid mole fraction and of our total. Okay, so we determined this was, and we want to use for non-N in this case, so we're going to work with 0.383 minus 0.3125, which was determined in orange up above. Okay, and this is minus our liquid composition, which was given in our question, 0.0246, is equal to an L, and our total moles was so we have 10 plus 22, so that's going to be 32 kilomoles. So that gives our moles of our liquid equal to And this is going to be 16.46 kilomoles for our liquid. Okay, so that brings us to the end of this example question and these notes. There is another practice to go through, so I'm just going to stop by each of the pages and have you work them out on your own using what you learned from this video and the previous example. All right, so I'd like you to try these questions out for yourself and get that practice in so you can understand how each of these equations work and how you can utilize them properly. All right, that is the end of today's video. I hope you enjoyed, and I'll see you in the next one.